All right, so we're back looking at example 3.6. We just found the functional form of the acceleration for part A. Now we are going to move on to part B. Find the instantaneous velocity at these different times. Okay, so we're going to say, v at 1 second. Okay, that's the first one. We're going to plug that into this equation. So it'll be 20 times 1 minus 5, 1 squared. Okay, so that's 20 minus 5. That gives us 15 meters per second. So you can go ahead and do this on your own, figuring them out each down the line. It's pretty repetitive, plugging those in. So I'm just going to write them down. V2 is 20 meters per second. V3, or sorry, not V3, but V of 3 seconds is 15 meters per second. And velocity at 5 seconds is negative 25 meters per second. Okay. So you can go ahead and check those on your own. Then part C, find the instantaneous acceleration at those same times. So now we're going to do something similar. So the acceleration at 1 second is going to be equal to 20 minus 10 times t, which is just 1 in this case. So that gives me 10 meters per second squared. Okay, again, I'm going to just write them down. You can check them on your own. Acceleration at 2 seconds is 0 meters per second squared. Acceleration at 3 seconds is equal to negative 10 meters per second squared. And the acceleration at 5 seconds is negative 30 meters per second squared. Okay, so that is the instantaneous velocities and accelerations. Okay, now for part D, it asks you to interpret your results of C in terms of the direction of acceleration and velocity vectors. Okay, so looking at part C, okay, you can see that at 1 second we have a positive acceleration. Okay, so I'm going to say at 1 second we have a positive acceleration. Okay, and we also know that that means we have a positive change in velocity. Okay, so it's not that the velocity is positive, it's that the change in velocity is positive. Okay, so again, not that the velocity is positive, but the change in velocity is positive. Okay, so then at 2 seconds, we have no acceleration. That means we have no change in velocity. So the velocity remains constant. Okay, so this can also be constant velocity. Okay. At 3 seconds, we now have a negative acceleration. So see how it has negative meters per second squared? Okay, that means we have a negative change in velocity. So now the object, or the particle, is now moving in the opposite direction as it was before. Okay? Then at 5 seconds, again, we have a negative acceleration, and therefore a negative change in direction. Okay? All right. So I'm going to go ahead and move on from this example. If you need to spend more time on it, feel free to pause the video, maybe look in your textbook if you want some further information about this problem. All right, so now we want to look at motion with constant acceleration. Okay, and we're going to look at notation here. So we're just going to call delta t just t, because usually when we're looking at the change in time, it's just going to be the time elapsed. Okay, oh, whoops, sorry. Time elapsed here. Maybe I'll write it over here. Okay. With the change in position, we're going to say x minus x naught rather than x final minus xi. Okay, so we're just going to call it x minus x naught. It's a little bit easier. Same thing with delta v, v minus v naught, and a. Again, we have constant acceleration now. So we're going to say it's just equal to a, and a is a constant. Okay? So we're then going to say that v, or our average velocity here, is our change in x over change in t, or just x minus x naught over t. Okay? And so we're going to rearrange these equations in order to describe our motions. Okay? We're going to get what's called equations of motions. Okay? Equations of motion, I should say. So if I were to take this equation here and solve for x, this is what I'll get. So I can, it would be v, if I move over my t here, v times t equals x minus x naught, then solve for x, and we get this equation here. Okay? Okay, so now we have this next equation here, and that's going to be the average velocity. And so that's quite literally where this equation here comes from. It's just taking our initial and our next velocity v, dividing them by 2. Okay, that's just the average velocity. Okay, and just to show you the difference of having a constant acceleration versus a varying, so this is acceleration, varying acceleration. Okay, our constant acceleration means that our slope of a velocity versus time graph will be constant. If the acceleration varies with time, this graph will be different. So this is an example of that. Okay. All right. So now we want to look at final velocity. Okay, so let's start with our acceleration, and it's going to be constant. Okay, that's going to be v minus v naught over t. We can solve that for our velocity, our final velocity here. Okay, so again, take your t, multiply it over here, and then solve for v. Okay. Now we can look at this and make some observations. So first thing is our final velocity, which is v here, depends on how large our acceleration is and how long it lasts. So it depends on the acceleration and the time. Okay. If this acceleration is 0, okay, that means our final velocity is equal to our initial velocity. Okay, so that means v equals v naught, or that our velocity is constant. Okay, if acceleration is 0. If the acceleration is negative, the final velocity is then less than the initial velocity. Okay, so the velocity decreased. Okay, or v is less than v naught. Okay. All right, now looking at final position, we have this equation, and we can plug it in to, let's see, where did this, whoops. So we have this equation, right? X equals x naught plus vt. So x equals x naught plus vt. Plug this guy in for v. You get x naught plus v naught plus at, and that's times t. And so then you get this equation here. So this describes our position, our final position. Okay. Now let's make some observations about this. Okay. The displacement, okay, depends on the square of the elapsed time when the acceleration is non-zero. Okay. When we have some acceleration. If the acceleration is 0, the initial velocity equals the average velocity. Okay, and so then it becomes as so. Okay. All right, so these are equations that describe motion. Okay. Now we have the final velocity from distance and acceleration. And so this is the same as saying acceleration equals delta v over t. Okay, that's the same thing, just with a little bit of rearranging. And then we get this next equation here. Okay. With a little bit of manipulation of the other equations, and we observe that the final velocity depends on how large the acceleration is and the distance over which it acts. Okay. For a constant acceleration here, we notice a car that is going twice as fast doesn't stop in twice the distance. It takes further to stop. Okay, this is just one of the observations that comes about from this equation here. Okay. All right, if you want more detail on how these equations come about, they may go through it a little bit more in the textbook. But for sake of time, I just want to go ahead and list them out for you to be able to use. Okay. Again, these are all just manipulation, plugging one into another and kind of solving them that way. Okay, they're all closely related. Now, let's go ahead and do an example. This is 3.7. An airplane lands with an initial velocity of 70 meters per second, then decelerates at 1.5 meters per second squared for 40 seconds. What is the final velocity? All right, so we know our initial velocity, v naught, is 70 meters per second. Our acceleration is going to be 1.5 meters per second squared, but notice that it says decelerates, okay? So the fact that it says decelerates indicates to us that we have a negative in front of our acceleration. Okay, so that's going to be a negative 1.5 meters per second squared. And our time is 40 seconds. And it asks what our final velocity is. Okay, so looking back at our equation here, we can use this equation here. V equals V naught plus AT. Okay, V equals V naught plus AT. So we can go ahead and plug these values in. Okay, and then use our calculator to solve it. Okay. And we get that our final velocity of this airplane is 10 meters per second. Okay. All right, so that was example 3.7. Let's move on to examples 3.8 and 3.9. They are closely related, so I went ahead and combined them. Okay. I will go ahead and state the question, and then in the next video we will have to continue it. So it states dragsters can achieve an average acceleration of 26 meters per second squared. Suppose a dragster accelerates from rest at this rate for 5.56 seconds. How far does it travel in this time?